In this video, I would like to review some of the properties of the graphs of quadratic functions. We are assuming that you are already somewhat familiar with the graph of a parabola, and so this will be a quick overview of some key points. If we have a quadratic function written in vertex form, then we know already from an earlier video that the vertex is simply the numbers h and k. We can also say that the equation of the axis of symmetry is the vertical line x equals h. This is a vertical line that passes through the vertex, and the parabola is symmetric across this line. The reflection looks the same on both sides of this line. We also talk about the maximum or minimum value of a function, as discussed in an earlier video. That also corresponds to a value of the vertex. That is simply the y value k. And we can determine whether it is a maximum or a minimum based on looking simply at the very first coefficient in our function. If that first coefficient is positive, the parabola opens upward. If it's negative, the parabola opens downward, and then we have a maximum value at the vertex. Let's practice sketching the graph of a quadratic function by plotting a few points first and then showing the picture. So if our function is y equals x minus 1 squared minus 4, I already know that the vertex is at 1, negative 4, and I could show that point on the graph. It's also a good idea to show the y-intercept and the x-intercepts. Those are important points on the graph of any function. For the y-intercept, we can let x equal 0, so I can simply plug in an x value of 0 and solve for y. I get y equals 0 minus 1 squared minus 4, or y equals negative 1 squared minus 4, which equals 1 minus 4, which equals negative 3. So what we are saying here is that when x equals 0, y equals negative 3. That is a point on this graph, and we can plot that point. For the x-intercepts, we do the opposite action. We let the y value equal 0. So we can set up the equation x minus 1 squared minus 4 equals 0, and we want to solve for x. We want to find any x values where this is true. There's a couple of ways to solve this equation. One way is by taking a square root, since it is already written in perfect square form. So I can say x minus 1 squared equals 4, and then take a square root of both sides. X minus 1 equals the positive or negative square root of 4. I need to consider both solutions here. And when I solve this, I can say x minus 1 equals 2, or x minus 1 equals negative 2, which means x equals 3, or x equals negative 1. So there are two different x-intercepts here. One of them is 3, 0, and the other is negative 1, 0. Those are also important points, so let's show those on our sketch. This is enough information now to draw a very accurate picture of the quadratic function. It passes through the vertex 1, negative 4, and through the x and y intercepts shown. The axis of symmetry for this parabola is the vertical line passing through the vertex. That is given by the equation x equals 1. I would also call this output value, this y value, a minimum value. It's at the bottom of the function. So I'd say there's a minimum value of negative 4. And that affects how I answer a question about domain and range. Before we move on, let's look at the domain and range of this function. The domain of any quadratic function is from negative infinity to positive infinity. It is defined for all values of x. However, the range is limited, and that depends on the maximum or minimum value that you see. For this example, the range extends from negative 4 to positive infinity, from the smallest y value to the largest y value. Now, I'd like to look at one final example and sketch the graph of a quadratic function using a different strategy that we discussed in an earlier video. And I want to make some connections here between what we already know about transformations and what we're explicitly saying now about finding the vertex and the x and y intercept of a graph. So I could sketch a graph of a quadratic function simply by using transformations as well. Let's apply what we learned in an earlier video here. So this -4 at the end means we'll take the original toolkit function and we'll move it 4 units down. That affects y values. This +2 in parentheses affects x values. We'll move all the points 2 units left. And this negative sign on the outside is a reflection, a vertical reflection, across the x-axis. So if I simply keep in mind those 3 transformations, I should be able to sketch the graph of our function without identifying any other points. First, let's imagine that vertical reflection. I'm showing here the graph of y equals x squared. That's our toolkit function. And first I'm going to take it and reflect it across the x-axis. So I want to identify a couple of points here. We have 1, -1, and we have -1, -1. Now for each of those points, I also want to think about shifting them 2 units to the left and 4 units down. So I take what used to be the vertex at 0, 0, and I move it 4 units downward and 2 units to the left. It is now at -2, -4. I take this point of -1, -1, and I move it 4 units down and 2 units to the left. It's now at -3, -5. And I take this point of 1, -1, and I also move it 4 units down and 2 units to the left. It's now going to be at -1, -5. I could continue doing this with other points on the function, but I think this is enough to show a rough sketch of the new graph using transformations. Here's what our new picture looks like. Now this function does not have any x-intercepts. It never crosses the x-axis. There is a y-intercept here that I didn't explicitly identify, but you should be able to go back and do that using algebra if you would remember to let x equal 0 in order to identify the y value of that point.